All right, folks, welcome back. I hope you all had a wonderful spring break. It's great to be back. As a quick reminder, I'll talk about homework upcoming, but we do have the exercise that began before spring break due tonight. We'll get into some more data structures today. So today we're going to be focused on sets and dictionaries, which will round out our fundamental data structure unit where we've seen tuples, we've seen lists, and now we're looking at two other kinds of data structures that have different properties, serve different purposes, called sets and dictionaries. We're going to jump straight into a warm-up diagram, and I'm actually going to use, I think this text is a little bit bigger. I will say that these slides are on the course site, so if you're on an iPad or if you can't read this and you're on a computer, want to trace through this, let's go ahead and try tracing through this example. And then there are a couple of interesting follow-on questions to discuss with your neighbor once you've got it. The what?
The slides.
I want to point out the two questions here, the follow-on questions for, this is sort of the interesting point of this particular exercise and opening with it. How many times does line 9 get evaluated? Try counting that up in your example. Another question to discuss is, what is this function actually doing if you were trying to describe what it's doing in English? And the name of it gives a hint if you've taken a discrete math course. 2 more minutes. All right, let's talk through this. So we've got a function definition, intersection, and the use of it takes 2 lists as an input. Would someone like to try and describe in English at a high level, what do you think is kind of, what's the point of this function? What's going on? What do you expect the result of this function output to be given 2 lists of strings based on its implementation? All right.
Like the elements that are found in both strings?
Yes.
Or in both lists?
The elements that are found in both lists. intersection, or what are the common elements of both lists of strings. And what we're seeing is, in order to do this with a loop, we've got to look through each item of one list and then go and look through each item of the other list and see if it's in it, right? So that is the outer loop's job, is trying to see, okay, let's move through every index in list A and consider its item. And we want to see whether or not this item at index A is in B. And in order to do that, well, then we've got to go look through every item in B. And we're using a little trick here. Notice we're setting up an extra variable, saying if we've found the current item that we're looking for example, item B occurs in both, or string B occurs in both. So if we're at index 1 of A, which would be B, and we found that element in bar, or the B variable, we would say, okay, it looks like this element does exist in both lists. We set this variable to true, and then when this inner loop goes back up, because we use this compound Boolean expression, we would stop looping. We could say, okay, we don't have to check the rest of the list. We found it. And this is a little shortcut. When we do find a common item, we're just appending it to some result and then ultimately returning that result. And for the purposes of discussion, this was a warm-up, and rather than, because most of the concepts found in this diagram are ones that we've been through, the result here would just be the list B, is what you would be looking for in the printed output. What I really wanted to talk about is, given what we've just said, that the whole point of this function is, given some inputs list A, we're going to look through every element, and then we're potentially going to have to look through every element of B for each element in A. How many times does line 9 evaluate? How many times are we potentially running this particular test? Or how many times did you run this particular test? Anyone want to call out an answer here? Yeah. 5 times. So it's very close to 5, right? And the reason why it wouldn't be 5 is because we've got 4 checks to make, right? So this is a quick off by 1. But your intuition is exactly correct. So line 8 would run 5 times, but we wouldn't enter the loop that 5th time, because there would be nothing for us to check against. Our index would no longer be less than what we were looking for. So you're exactly right for line 8, but line 8 is guarding us, protecting us from making a comparison that isn't valid. And ultimately, if we ran this with an invalid index, we would get a key error, or an index error, right? So if we checked an index that didn't exist, so we checked index 2 or of either of these 2 lists, we would have a problem. The intuition is for every, so this loop is going to run length of A times, right? The body of this loop is going to run the number of elements it has. We're having to check each and every element, right? This inner loop, potentially, in the worst case, and in this case it kind of is a worst case because we are finding the match at the end of the string. This is length of B, number of times. But because the inner loop has to complete for every outer loop iteration, this winds up having a multiplying effect, right? So this intersection algorithm, we could say runs in, generally runs length of A multiplied by length of B operations. And we'll call this check in here our key operation, where we're saying, does this exist in both? And if so, we're going to keep track of it and append to it. So you can kind of imagine, well, for an element, for lists where we've got 2 and 2, 2 times 2 is 4, but this starts to compound in a bad way, right? If we had 10 in each list, we would potentially have 100 different checks or 100 different iterations to move through in working through this diagram. What we're starting to touch upon is a fundamental concept in computer science called complexity analysis. And it's not really the focus of this course, but we introduce it in this course because it is foundational to computer science. And the question about complexity analysis is can we find a better way to implement an algorithm such that we don't have this particular outcome? And so if we imagine that if we generally call these both, like, let's say they're both the same length, they're length n, and if we have length n times length n, if we call the lengths of these both n, which is the number of elements we have n times n, which we know as n squared. And what we'll see is that when we have n squared algorithms, that means that as we add more items to it, our runtime grows pretty in complexity because our algorithm takes much longer to complete as the size of our input data grows. We're going to come back to, and one of the things we're going to look at today is a question of how do we improve upon this, and can we do better than this for this particular problem? And let me ask this question in the back. Yep. Great. So while not found is an interesting piece of this that may be a little trick that we haven't used before. So here, if we initialize found to be false, this would initially be what? Sorry, I'm having trouble writing this morning. While not false, and so on. Not false is true. So true and so it's basically a way of saying we're going to start this. We're saying we haven't found the item that we're looking for in list B yet. So we say that that's false initially. And while not false is effectively while true, so we're going to keep looping until we find this given element. And that's what happens when we set that to true. When we come back and test again in this while loop, not found would be false this time around because found is true. Yes, exactly. Yep, so this whole entire Boolean expression must evaluate to true in order for the loop to continue moving. So as soon as we find the element, we're saying stop looping. We don't need to check the rest of this. We know that this list is this element is in both lists, and we can continue on. Great, good question. Other questions? Yep. So that is exactly correct. You do keep looping while the inner, until the inner is no longer. So let's carry through with one quick example of this. So I'm going to jump right in, because I think this is a fundamental question, and it's a great question. All right, so I'm going to jump into a frame of intersection. And A will be ID 1. That's the list that has 0, 1 of A and B. And B is ID 2. And I would have already set these up in globals. I'm just jumping into this a little fast forward. Lister. and scribbly because this part isn't the important part, C and D. And then the interesting part of this question is what's going on with these two loops and how do we keep track of the state? So we set up a result, and I'm also ignoring my return address and so on. My result would be an empty list. All right, and then we set up index A. It's initially 0. While A is less than the length, while index A is less than the length of A, well, the length of A is 2, 0 is less than 2, that's true, so we go into this loop, and then we set up index B, and it's 0 as the first step of being inside this loop, right? We set up found to be false. And I'm using imprecise terminology here. We initialize found to be false, right? Then we reach this statement. We just talked about why this is going to be true initially while not found. So not found is true. And the second condition also needs to be true because this is an and. Index B, when index B is 0, is less than the length of B. Length of B is 2. So we would go into this loop. Now here's where we can kind of fast forward and say, OK, is A at index A, so A at index 0, that's A, is that equal to B at index B, that is C, so that is false. So we don't append anything. And then here, notice this is where it's really important, and the fundamental part of this question we finally arrived at is how do we process the syntactical nature of this loop versus this loop. So this inner loop is increasing B's index by 1, right? So now we've got B increasing by 1. We go back up to the top. We still haven't, not found is still true, and B is still less than 2. So we go in, we test. Is index A of 0? So that's A. Is A equal to B? That's also false. So we skip over the while loop body. We increase index B to be 2. Now we say, well, not found, that's true. And 0 is 2 less than 2. That's now false. So this evaluates to false, right? And this is the point at which we're done with the inner loop, right? And we continue on. And so when we continue on, what we're now saying is increment index A to be 1 more than its current value. We go back up to the top, and here's where we test is index A, which is 1, less than the length of A, which is 2. That's still true. And here's where we reset, right? So here's where we would say, I'm going to use green here, or maybe blue. Index B has been reset to 0. And found it's false. You could imagine it being reset to false, but it's the same thing either way. And then we would have to go through that loop again. And we would go through that loop again until we found that B was in both and continue on. Is that helpful? OK, great. Yep.
I had written found to have the value of 0 instead of writing false. Would that be wrong?
I would encourage where we have Boolean values to try and maintain right in the Boolean the value for that. Yeah. Because if you went to print that value out later in Python, you would see false printed. And it is keeping track of the distinction between those two. Good question. Other questions? All right. So what we're going to do next is, well, actually, before we go on to what's next, I want to mention to you, I'm actually going to switch my slide deck, an operator that we didn't talk about yet, but we're going to need to talk about today. It's called the in operator. It turns out you can use this cute little operator named in to test what we were doing in that inner loop before, right? So we can test, is A at index A in the list B? And so the in operator tests for the existence of some item on the left-hand side. So this would be our item. And this would be the list that we're testing. Or I should make this more generic and say this is the collection that we're testing. And this is very appealing because it's very simple, right? We just avoided that whole loop, didn't we? We didn't have to write another while loop in here and loop through everything. Well, the reason why we haven't talked about this yet will hopefully become fully visceral today, is that we really don't want you to ever use in with a list unless you know with certainty that that the list that you're testing, so B in this case, for the existence of some element in it, is always going to be bounded by a low number of elements, right? But if you don't know anything about B, if you have to assume that B could be any list, you really want to avoid writing code like this that tests for the existence of some element in a list, because there's no free lunch, right? Under the hood, this operator is still having to loop through every element in B to test whether or not some index is in B. So you haven't really gained anything. If we had 100 elements in both, we would have, if we had 10 elements in both, we would have 100 operations total. And so it's still n squared, that multiplier effect, right? So generally, when in doubt, don't use the in operator with lists. Right, we're about to learn about sets and dictionaries where you will use the in operator, and it doesn't have this fundamental problem because of some interesting different properties. But with lists, you generally want to avoid this unless you're certain. You know this list is always going to have, less than 1,000 elements or something like that is typically OK. But even 1,000, you want to be careful with how you're making use of it. Generally, try and avoid using in with lists. If you can, especially inside of a loop like this. So how do we test for the existence of something in a collection of values? And this is going to be the introduction to a new data set, or a new data type called a set. And I want to just write some fundamental notes down, and then we're actually, after we take a few notes, going to go check out and play with this in some code. So a set is a collection of items. And I'm actually going to be a little bit more precise here and say of immutable items that cannot have duplicates. And is unordered. Right? So what springs to mind as something that's different from lists right off the bat? Yeah, we'll go in the front here. The things have to be immutable. Yeah, so your items need to be immutable. So that means you can use integers, strings, tuples, and so on, but you can't use lists. Yep. Lists can have duplicates, whereas sets have unique members of the collection. So lists, you can have a list of A, all individual strings, no problem. A set, you can only have one string A in a set. Absolutely. One other key difference. Yep. Lists have order. Lists are sequences. And the sequential nature of the items of a list mean that you can you're guaranteed some ordering of those values once you've established or initialized your list. Whereas a set, you have no guarantee on the order of items in the list. And you're probably thinking, well, these trade-offs seem a little bit less useful than a list, right? It seems like a list has more capabilities and more flexibility. We can put immutable items in it. We can have duplicates. It's ordered. These are all properties that seem quite nice. But what we've just looked at is one of the fundamental downsides to a list, is that testing for the existence of something in a list takes looking through the entirety of the list to know whether or not it's found. The beauty of a set is that once you've established a set, and thanks to some underlying implementation that's quite clever, and in fact, if you're curious about this and it strikes your interest as, wow, how is it that they're able to pull this off underneath the hood? It's entirely the focus of the next course that we're in, that you would take in computer science, COMP110. But the big upside of a set is that testing for the existence of an item takes only one operation, regardless of set size. Right? And we're waving our hands a bit. There's, of course, the use of the word operation is something we're using sort of fluidly. But in our concerns, one method call, when we make a method call to, or use the in operator, and I'll actually make a note of that. You can use the in operator with a set, and you have to use the in operator with a set because there's no way of indexing it. You wouldn't index it. Your items are not guaranteed to be in any order. So you'd use the in operator to test, is some item contained in this set? And what's beautiful is that's instantaneous. It's one operation. It's like checking, it's effectively equivalent to checking, is index 0 of some list equal to something else? It's just about the same, for our purposes, set of operations under the hood that need to happen in order to pull that off. And so these are some key trade-offs. We have these properties that are a little bit different about how we think about sets. You know, they're unordered. You can't have duplicates. Your items have to be immutable. But we get this really nice benefit of, well, if we had some algorithm where we really wanted to see, does some item exist in some big collection, it's much, much more efficient for that type of a purpose. And you're probably wondering, when would you ever have some type of lookup like that? Well, maybe you're implementing Connect Carolina and you want to see, does some PID or does some PID exist in the database? And so you would maintain your PIDs in a set, and it would be very fast to look that up. Whereas with a list implementation, you'd have to scan through every single element. Maybe you could use some clever algorithms because we know that they're ordered in a serialized way where we effectively have our own serial numbers. But nevertheless, it's a much more efficient operation. All right? So before we jump into describing or playing with these in actual code, let's just set up a few notes on types and how to construct and initialize a set. So the type of a set in Python is specified as set T, where T is immutable item type. Right? So if we wanted to say that we have a set of names, we could have a set of str. Just like the other types that we've encountered, such as int, str, and bool, list, we can set up an empty set with the set constructor. So this is the empty set. While the items of a set are immutable, the set itself is mutable. We can add items to the set. And a way that we would do that is, rather than append with a list, we can add to a set. So names.add, and I'll add my name. This would ultimately add my name to the set. Now again, it's not in any order, and we'll look at how we might work through every item in a set in just a moment. But once we do that, we could then test something like Chris in names. This is an expression that would evaluate to true after I was added to the set. Whereas, you know, foo in names would be false. The last note that I want to take here is, yeah, question in the back. Great question. When you're adding something to a set, where does it put things in that set? So I'm going to answer this in two ways. The first way is you should think of this almost like, you know, a giant circle where something's added here. If I added another name like Sally, you can think of this as a very fluid, no real order is guaranteed, right? Now, you might be asking, well, what if we were diagramming this? What I'm going to tell you is we're not going to diagram sets because sets, what they're structured as under the hood, are interesting and complex enough that we don't want to, if we wanted to, we would just give you a table without any index, and you'd have to remember that, hey, you can't expect these to be given back to you in any order, and it's going to be random. But they are a fundamental part of something we will be diagramming called a dictionary, which we'll come to next. But conceptually, you should think of it as just an unordered collection of items, and the only thing we'll see some other operations in just a moment. Like we can effectively do Venn diagram style operations of what are the common elements between two, what are the differences between two, things like that. But generally, conceptually, you think of them as unordered and just sort of floating around. In some disciplines, you'll see these called a bag. It's a bag of values, and maybe we can pull something out of a bag. There's a question here, yep. Is add the same thing as append? Conceptually, they're very similar. Both are adding some or inserting some new value into a collection. And for the purposes of a set, that's how you get a new item into it. For the purposes of a list, append is how you get a new item to the end of it. So they are very conceptually similar. We are adding something to a collection, but they're not exactly the same because they're two different data structures. Yep. Yep, question here. What happens when you print one of these out? Great question, and we'll try this in just a moment. So this gets to the last note I want to make before we jump into code. So what happens if I'm going to add one more name here. If we printed names at this point, the output would be what we call set literal notation. So we've seen list literal notation. Set literal notation is the curly brace. And then, you know, there's no guarantee on the order of these. Where's my? So I could have Sally first, maybe. And Chris second. But you're not guaranteed that. You could run the program multiple times. You could get back different outputs. But this does give us an example of set literal notation. And so just like with list literals and int literals and str literals, we can write a literal like this in our code. We'll see one in just a moment. And this is how we would initialize a set with some elements in it. I will mention, and we'll come back to this when we get to dictionaries, you can't write an empty set literal. If you want to start with an empty set, you have to use the set constructor without any parameters. And we'll talk about why that is in just a moment. All right. So let's transition. And we're going to jump into some examples in VS Code. And I'm going to set up a file that I'd like you all to copy so that we can play around with sets a little bit. So I've set up a directory that is class 13 and a file in that called sets.py. And I'll have you try and jot down this code that we're starting with. So the file that we're starting with, if you create a directory in lecture called CL13 and name this sets.py, or if you want to put this wherever it makes sense in your project, that's fine. And go ahead and jot down what we've got here, where we've set up some string constants and then some sets, which include these string constants. And I've gone ahead and opened up Trailhead to the REPL with these so we can play around with them. 2 more minutes on this. And if you want to try using the in operator to get a sense of how it works, I would encourage trying that. So you can try, vampires in immortal, vampires not in immortal. So not in is the opposite of in. And you can try this with some other strings and values as well to get a sense of how working with a set using the in operator works when testing for the existence of a value. Thirty more seconds, and then we'll continue on. All right. So we've set up a few sets. And these sets, while they look ordered in our editor, you'll notice that in the editor we had vampire, zombies, Santa as immortal. But when I loaded this code, we have Santa, vampires, and zombies. If I refresh this particular page, we see vampire, Santa, zombies, and Santa, vampires, zombies. And you can kind of see that when we actually load a set and we try and revisualize it, we don't have any guarantee as to the order in which these items will appear in our set, because that's kind of the whole point. Now, of course, to show them on the screen in some way and to make a textual output, we're having to, at some point in time, say, OK, here's the order for purposes of display. But again, there is no implied order. Just like lists, we can get the number of items in a set with the length, with the len function. So len immortal, we see that that's going to be 3, as you would expect. So that's one way of testing for the existence of a list or of a set. And I've got to condition myself not to saying list. We can also remove items. And here's one place where we want to be careful. So your intuition might be, well, why not pop an item? So let's try it. So immortal.pop Santa. And you'll see that we get an error because for the set data structure, the pop method is different from the pop method for a list. It doesn't take any arguments. So what does it do? Well, it's something that in some cases might be useful. It takes one item from the set and returns that back to you, and it removes that item from the set. So you'll notice that now my immortal set no longer has Santa in it, but we had returned Santa from calling this pop method. So if you wanted to, you could loop, if you wanted to write a loop of, and you didn't care about mutation of every element in a set, you could loop while the length of the set is greater than 0, pop the next item, pop the next item, pop the next item, and do something with each item in a set in that way. That's one way of looping through a set. We'll see a more common way that doesn't involve mutation shortly. Right? I mentioned to you, though, that so the key win for working with sets is we can test, is Santa in immortal, and that gives us a true or false value, and that's a very fast operation. This is the whole point of sets. They give us a very quick lookup. As a part of this, they have built-in methods for things like intersection and union. So union is combine these sets. So immortal.union emerges at night. And we see that the union method brings two sets and combines them. Now you'll notice that because there aren't duplicates allowed, even though there are some items contained in both, like Santa and vampires, there's only one entry for each of those items in the resulting set. Right? Similarly, if we wanted to take the intersection of, I'll also mention that there's a special, Python likes to use little operators that are cute. And so each of these operations that we're looking at that's very common with a set, so union is the single vertical bar. And so those are the same thing. Immortal.union emerges at night is the same as immortal vertical bar emerges at night. So it's a slightly nicer syntax for unioning two sets. The algorithm we just looked at was intersection. So we can do something like immortal.intersection emerges at night, and see that Santa and vampires are in that set that are common to both of these sets. Again, a very fast operation that only needs to effectively, is bounded by the size of one of the sets, which is pretty cool. Again, this operation also has a shorthand. So immortal intersections with emerges at night. And that's, again, the same operation with the and operator, so, or with the ampersand. So vertical bar with sets is union, ampersand is intersection. And just like with addition and subtraction, these operators do compose. So if we wanted to see what is the intersection of immortal merges at night and invades your home, and that's just Santa of these options, right? I mentioned to you that pop will remove a random item. If you wanted to remove a specific item, there is a aptly named method for that. So immortal.remove Santa will mutate the set that you're calling this method on and take that item out of it. Okay? There are other operations that you can take with sets, like you can find the difference between two sets. In fact, let's give one example of that. So immortal.difference emerges at night. I misspelled it, my bad. And we see that that takes what are the elements that don't exist. So Immortal has zombies, Santa, and vampires. If we remove all of the elements from Emerges at Night, all we are left with is zombies because Emerges at Night does not have zombies. This works in the other way as well. Emerges at Night. Dot difference. Immortal. And if you could imagine what operator, if we had to pick like a mathematical looking operator, makes most sense for the difference, it's the subtraction sign. So Immortal, subtract, Emerges at Night is the same thing as difference. These operations on sets and thinking about sets is the bread and butter of discrete math. So if you take Math 381 or COMP110, you'll spend a lot of time thinking about mathematical properties of sets, and they translate into programs in this way. Right? Any questions on sets before we look at dictionaries? Yep. Great question. How do you think about orders of operations here between these operators? I would have to look it up to know what the implicit ordering is, but your intuition is absolutely right. Just put some parentheses around it, and that'll give you full control. All right. Yep. If there was no intersection, would you get an error? Let's try it out. So one of the best ways of answering a question like this is a fantastic question is, let's make another list of, or another set, I should say, of names. Set, stir, and let's just add one item to it. And if I now do the intersection of names and Immortal, which sadly I am not, or maybe gladly I am not, we just get the empty set. And so the empty set will have a length of 0. It is a valid set. It's just a set with no items in it. Yep. Yes, I should. That's a great question. And I should, to repeat the question, do you get a new set when you take the difference, or when you take the union, or the intersection? Yes, all of those operations result in a brand new set as the evaluation of that. Kind of like 1 plus 1 gives you a new number 2. We're not mutating there. The methods that do mutate are add and remove and pop. They will mutate what you call it on. Great question. All right. So let's add a new file of notes on dictionaries. So I'm going to set up a brand new file and notes on dictionaries. I'm going to switch my example over. So dictionaries are the last of our fundamental, very important data structures in this introductory computer science class. Oops. I'm going to switch my demo over to dictionaries. All right. So we've seen tuples, which are immutable sequences. We've seen lists, which are mutable sequences. We've seen sets, which are mutable but non-sequential and have some other properties. And now we come to dictionaries. What are dictionaries, and how would we think about them? So a dictionary is a set of key value pairs. I'm going to call it a map of key value pairs, where the keys are a set, and each key is associated with some value. Okay. So what do we mean by a map of key value pairs? I think this will be easiest to discuss with an example. So let's, and we're going to get some syntax here that's new, and as I'm jotting this down, we can talk through each piece of it. But let's just go ahead and set up a dictionary. So schools is a dictionary of stir to int, and it will be assigned a dictionary literal, where we have something like UNC is associated with 20,210 students. The string or key Duke is associated with the value 6,640 undergraduate students, and NCSU is the school associated with 2,254 students. They deserve to feel a little sense of victory every now and then. It was a very depressing game, though. So we've got a dictionary here, and we've just laid down some syntax that's brand new. So the first thing you'll notice is this type, dictionary, and then we have two types in here, not just one. So we've seen something kind of like this before when we've seen tuples made up of various types. But here we're specifying, and let's make a note about this. Type of dictionary is dict, and I'm going to write a capital V, capital K, and V, where K is the key type, and V is the value type. Right? So in our dictionary of schools, we have keys of type string and values of type integer. Right? And once we save this, we can see that, okay, we've got our dictionary literal over in our REPL, and we can start to interact with it. So the big idea of a dictionary is that it makes it very fast to look up some value associated with some key. So for example, if we wanted to look up schools UNC with a subscription notation, so the same notation we use to index a list, here we're indexing a dictionary, we see that it's associated with the value, or will evaluate to the value, 20,210, which is the number of undergrads enrolled based on Wikipedia's latest data. All right? Similarly, schools NCSU is 26,000, right? So notice this feels kind of like a list in that we have some index in a list that's just some sequential number. Here we get to choose what are our keys, and it's very fast to look an item up by its key. Look up a corresponding value by its key. For adding an additional entry to, let's make a note about this. So for adding a key value entry to a dict, we could say schools, and then UNCC is assigned, and I looked this up earlier today, 23,461. Right? So dictionaries are mutable, and the way, in a list, you had to explicitly append, which grew the size of a list. In a dictionary, you're able to assign to a brand new key straight away, and that's totally fine. Right? So now you would see after, remember our REPL is the state of globals after our file has been fully evaluated. So at this point, UNCC is now in this dictionary. We can test using the in operator, and this is a very fast operation. Does some key exist in the dictionary? So is UNC in schools? And sure enough, that's true. Just like with lists, where if you look up some value, or look up an index that doesn't exist, you get an index error. Here, if you look up a key that doesn't exist, you get a key error. So if we could tried Iowa, if we tried schools of Iowa, we see we get a key error, and Iowa is not a key that exists in this dictionary. Right? Dictionaries wind up being a really handy tool for many different scenarios. We'll see some of the classics very soon, and one of those is counting things, such as counting words in a file. If you wanted to count up the frequency of some word across some long string, you could break that string up into just its words and have a list of words, and then count each word where a word is the key, and then the number of times you've seen it is the value. I should mention that we can increase this. So let's imagine that we wanted to increase enrollment at UNC We can use the operators we know and love with assignment, and relative reassignment. So if we wanted to increase our enrollment by 100, you can reassign values. So once a value is assigned to a key, you can reassign a new value to it. Notice, though, that because keys are a set, fundamentally, you can't have duplicate keys. Right? So that's one fundamental feature that you can take what we know about sets. We know that the keys of a dictionary form a set. And that means, therefore, that you can't have duplicate keys. It's also what helps to give us this lookup feature. It's a very similar under-the-hood trick and algorithm for making this lookup very fast. You can have duplicate values, though. So we could say, there's no problem with schools. Let's make Duke have the same number of students as we do. Actually, we'll make it a little bit less than us, of course. And it's actually the point of this demonstration should not be lost in rivalry. Here we're saying that Duke's assigned key value pairing is the same as UNC's. And it's totally fine, notice, for our dictionary to have duplicate values. But the keys are always going to be unique. You can't have duplicate keys in a dictionary. Probably the most common question about okay, so I've got this dictionary. How could I go and iterate through all of the keys and all of the associated values in this particular dictionary? And let's make an example of that. So looping through a dictionary. So I'm jotting down some notes here, and let's actually describe this. So for school, in schools, print f-string, and then school. Actually, I'm going to make this okay. So value is schools. So this is a new type of loop. We'll talk about this type of loop more in coming time. But for now, it's very handy when iterating through a dictionary. Yep. Oh, thank you. Sorry about that. Test, there we go. I'm not sure if that happens in the future. I don't know how long that was going for. How long was I going for? Not too long? All right, yeah, please do always interrupt, because it's not only those in the back who wouldn't be able to hear, but it's also the recording. So what we're seeing here is a new type of loop structure called a for-in loop. And it's really nice. You're guaranteed to not write an infinite loop. So with the while loops we were writing before, you had to be very careful to avoid an infinite loop. If you forgot to increment your counter you could run into an infinite loop situation. Here, we're saying for each school in schools. Well, this identifier that we're using here is effectively establishing a variable. We're declaring a variable named school to exist inside of this loops body. And the semantics of this structure are that each time we go into this loop, school will be the very next key in our dictionary. Now, I said that the keys are a set in a dictionary. Dictionaries are slightly different in Python in that they actually do, you'll see, but you shouldn't depend on this because in most languages, and it's kind of a funky feature of Python, your keys will maintain the order in which they're inserted in Python. Generally speaking, the dictionary data structure, you shouldn't depend on that, and you should assume that your keys are non-ordered. But in Python, they actually are, so you're not crazy for thinking that they are always going to maintain the order you are inserting them in. But nevertheless, so what we'd see is school is initially assigned to UNC, which we see that. And then in the body, we're saying, OK, let's just set up a new variable. And actually, I should have typed this variable. My bad. So variable, this is a declaration. It's a variable value int, is assigned the lookup of what's the at index school or at key school, which in the first instance is UNC. What is its value associated? So we look in the table. UNC is associated with 2030. Or 2,310, we print that out. The next time we loop, we're moving on to the next key, the next key, the next key, and so on. So it is possible to loop through every key in a dictionary, and this is how you would do something like that. Yep. Great question. So it's initialized. It's always going to be inside of this loop body. You have a guarantee that it's always going to have a value that is a key. And for the purposes of dictionaries and Python, it's going to be in the order that you inserted those keys. Yep. So it will always be filled with initially the first value, and so you see that printed out here. So when we print out school the very first time, it's UNC. Now I want to mention, and I'll come back to this question very briefly, if I were to rename this symbol. So if you ever want to rename a variable in your editor, a really handy feature is you can right-click on a variable name and rename this. I could rename this to S, and this would work in just the same way. That first, the identifier that we place after the for keyword, so for some identifier, that identifier we get to decide for our purposes of writing the program what that is, just like we do variable names, and it's just a variable name we're choosing. You generally want to make it meaningful, so school was a better name here than S, and I might actually change it back for that reason. But yeah, so what's the question here? What line is telling it to move on to the next key? Great question. So just like a while loop, when we reach the bottom, we go back up to the top, and it's just in the nature of this for in statement that you know you're moving on to the next key. You're moving on to the next key. Great question. I want to mention, because we just talked about this, in this context, we should also mention it over in the set example. So if you pull up your set example, you can also iterate through each item of a set with for in. So for item in immortal, print item. If I tried switching my examples, you'll notice that when we run this, again, because of the nature of sets, you're not going to get the exact same output every time. However, you are able to iterate through every item in a set using that same syntax, right? And again, we're choosing item. Item didn't have to be named item. It could have been type of character or mythical character or something like that. But it's the same semantics nonetheless. We'll iterate through each item once in this set, and you don't have to worry about the assignment or the updating or the indexing. That's happening automatically on your behalf. Right? The last note I want to make about dictionaries has to do with removing items, and that is very similar to lists. So let me go back to my lecture demo, sorry. All right. So I'm going to actually do this in the REPL. Here, we can pop values, and we do pop them similarly to lists. Right? So it's the same idea of schools.pop Duke. And now we see Duke is no longer in our dictionary in globals, schools.pop NCSU. It's feeling like the tournament already. UNCC didn't, I don't think, did UNCC make the tournament? No. So we can pop them as well. And you get the point. You're able to pop via a key as long as that key exists. And that pop method does return to you, as we're seeing here, it does return to you the value that was associated with that key if you wanted to use it for some reason. But otherwise, it's removing it from the dictionary, and now we're down to just the school remaining. The very last quick demo I want to show you is accessing just the set of keys or just the list of values or what we can see as a list of tuples of all key value pairs. So I think it's worth just making these in notes so that we can see the output of this in just a moment. So get a set of all keys. So keys will be set stir is, we use the set constructor here and ask for schools.keys. We can print those keys. Get a list of all values. And finally, get a list of tuples of all pairs. So you commonly would like to have access to just the keys or just the values. And sometimes it's useful to have a list of the key value pairs, and you can get that back in tuple form. And for completeness of demonstration here, I just wanted to add these. I'll mention that you can go back and forth between a list and a set by using the constructor. So if you pass a list to a set, you can effectively make that set out of the list. Of course, if you had duplicates in your list, they would be lost in that conversion. So I'll bring that up and leave it in just 1 second. But the very last slide to mention here is that example we started with where we had this very innocuous looking in. If we replace that with a set, so notice that B is a set in this case instead of a list, we would have orders of magnitude different performance where how we started without knowing what sets were and how to make use of them would take 1,000,000 operations, and with them would take would take 1,000,000,000,000 operations. With sets, we can do something in 1,000,000 operations. We'll talk about this more on Thursday. No submission for today. We didn't get to it. Sorry about that. I'll take that off of Gradescope. That's fine.
Hello. I noticed on the grade scope we had a CL.
I just deleted that, so
Okay,
you're good.
cool. I was like, it's doing like 3 seconds. I
Yeah,
don't know
yeah,
what
sorry.
to do.
Yeah. Have a good one. You too.